Welcome to our video on parametric reliability in DFRSoft. Uh, so we're going to talk about parametric reliability analysis. First, we're going to have a little overview to explain it. The advantage of doing parametric reliability, a lot of people, engineers, do parametric reliability analysis, but what they do is they do basically a catastrophic analysis of it. So we're going to explain how to do that, where you can reduce your sample size, you're going to save time, you're going to predict failure before it occurs, so you don't actually have to reach the parametric threshold and do your catastrophic analysis. You don't need to test a failure. That is, you have lower stress levels, you can be more accurate in your predictions, and you can also provide quicker feedback on your design improvements. The key is to have a knowledge of the aging law. So basically, there are two ways to do parametric reliability analysis. The first way is your devices will drift out of specification, and you might have a number of them on life test, and at the time that it drifts out of specification, you record that time and you do your catastrophic analysis like you normally would when devices fail. The second way is the more intelligent way, which is what we're talking about today. This way is the best way to use if you have a knowledge of the aging law. If you don't, then you go back to, you're stuck with your catastrophic method. So here's an example. We have a resistor that's drifting in time, and there's some power law for that. And in this case, there's a number of them, and they drift out of specification. You can see the fractional failure that's occurring over time. That is being done, and as long as you fit your distribution, you can actually predict this. So you actually can be testing over here, and you don't actually have to record your times to failure. You might be testing only this much, but you have a knowledge of your aging law, and you can predict how the distribution is going to cross this threshold, so you don't actually have to reach that threshold during your aging, and you can have a more accurate prediction. And you can, so this is a knowledge of how that would occur later in time. Notice your distribution can drift in either direction, positive or negative. Now, basically what you're going to need with your aging law is you're going to need to make a transformation from your time domain to the parametric domain, and DFRSoft does that for you, so you don't have to worry about that. So this is just some of the equations that are in the background, and here's an overview between your catastrophic analysis and your parametric analysis for your CDF, for example, and your failure rates. So basically, let's say we have a knowledge of our aging model. Now here's some very common aging laws, the two that are in DFRSoft that allow you to fit your data to it: the power law for time and the log time law. The power law is typical for, say, thin film resistors, diffusion times, corrosion, that sort of thing. The log time aging law, which is your 1 plus B time times the A outside. Crystal frequency drift, primary battery life degradation, transistor gain change, FET transconduction loss, creep, primary and secondary, chemiabsorption, gate oxide stressing, and corrosion of thin films. You can also in DFR do user defined. Now DFRSoft also uses an optional Radius model for the acceleration factors. How to fit your data in DFRSoft. We're going to go over that, but basically what you're going to need to do is you're going to measure your devices, say, over a 1,000-hour period at an elevated temperature, and you're going to record your drift and put that in percent change. And DFRSoft explains how you do percent change in DFRSoft. Let's go over to DFRSoft and see how we do parametric reliability analysis. You can download our trial copy, or if you have DFRSoft, you just simply go down and you scroll to then the 2013 version. It's not in the 2012 version. You can click over to your parametric reliability section, and here we are. And there's about a 4 or 5 step process. And so in DFRSoft, step 1 is the first thing you're going to do is characterize your distribution. So we need to know what the mean and the sigma are. So you're going to hyperlink over you're going to say you're measuring resistors. So basically you're going to put your resistor values in the green squares, and this is the quality page we hyperlink to down below in the quality page, and we have a mean, we have a values, we put our values of our resistance, we measure say the 30 devices we're going to put on live test, and we measure the resistances, say 5 ohms, 4 ohms, 3.2 ohms, 4.8 ohms. Those might be the resistances at room temperature, and we put those in the squares here. Then we look at our graph. There's two graphs that are of interest here for what we're talking about. It completely characterizes your distribution, and this is a regression analysis for your normal distribution. It gives you your rho for your fit for your normal distribution, for your mean and your sigma, and it's a very good fit for the normal. You go down and you look at your log normal, and you can see it's not a good fit. So for this data that we entered here, it was normally distributed, not log normally distributed. Now you take your mean and your sigma and you go back to your parametric section in DFRSoft, and the parametric section, go to step 2. Now we have our mean and our sigma. The next thing is to fit your data, your live test data. DFRSoft makes that easy if you use one of those two laws that we talked about. You put your aging times here, and you put your percent drift in percent drift there for each device. Up to 5 devices it'll fit. If you need more, you can contact us. That's the basic. Here's the power law fit model right here. And it gives you your average value for A and B. The same thing for your log time model. The only difference is DFRSoft uses a state space model to fit it. It's not a simple model to fit. So you put your times here for your drift and your device shift, and then you have to press on the macro button, and it fits your data, all the 5 devices, and it gives you your fit down below. It shows you your fit, and you can see the difference between your log, the power law aging model for positive powers, and for your log time aging model kind of bends that way when we're talking about positive shift. And it gives you a summary of your average values for your A and B, and that's what you're going to need. So you go next and you finalize your model in section 3. So you put your constant values of A and B that you're happy with, and then you select the model. If you're using the log time model, it's provided here. And the next thing is you find your acceleration factor. If you're using the temperature acceleration, you put that in here. Here we have 1 EV. You put your test time and your use time, and it gives you an acceleration factor of 25. Now you might have some other stress, so don't worry. You can implement that other kind of stress. So this is the area where we're going to find out about our fractional failure over time. Now we enter our mean that we found at room temperature and our sigma, and we put our parametric limit. So say the mean is 4 ohms for the resistors, and our parametric limit is 5. Now DFRSoft tells you if it's a 5, it'll be 25% change would be the parametric limit. So you can play around with that. Say you want a 20% change, you can change that to say 4.8, and that's about 20% change. It shows you that. So 4.8 would be your failure threshold, and then you have to tell it whether you're drifting in a positive direction or a negative direction with your. So if your distribution is increasingly going positive or negative. And then the next thing you need to do is tell it whether you want to put a stochastic model for sigma. Sometimes sigma broadens over temperature, and DFRSoft has a little model for that. It's not a big effect, so don't worry about that. If you don't want to model sigma that way, just put a 1 there. And then you enter your acceleration factor. The next thing is you're going to put the time of interest. So if we're talking about use conditions, because we put our acceleration factor, you might be interested for the first 10,000 hours. So you can plot from maybe 1,000 to 10,000 hours here, or you may want to find your mean time to failure. So basically DFRSoft will display the results here. And also you want to indicate whether you're working with time in hours or months or years here. And that must be the same as when you found your parameters A and B. So the next thing you want to do is look at your table, and you can see highlights for you the 50% points here for the fractional failure. So in this case, it was about 6,000 hours is the mean, and it gives you the reliability, the failure rate, and the failures per million hours and that sort of thing. Also gives you the graph for your fractional failure over time, whether it's the mean or whether it's the normal or the log normal distribution. So that's basically it, and there's a little calculator below. If you want to know some other time, you can put in say 5,000 hours here, and it'll tell you the values, 16.9% failure there. So thank you for the opportunity to explain parametric reliability analysis in DFRSoft.